Hello everyone, good evening. All right, so let us get started. Let us have a quick recap what we have discussed in the last week. Right, so we have discussed in the last week, we started a discussion with the statistical module. So as part of that, we discussed about what is the statistics, right? And what are the different statistics that are available. We discussed about the descriptive statistics. And so we have two kinds of statistics, descriptive statistics, and we have inferential statistics. So we have started discussing on the descriptive statistics. As part of that, we discussed about measures of central tendency, measures of variance, and we discussed about various visualization techniques. So that is what actually we discussed under descriptive statistics. As part of this, we discussed about various visualization techniques such as bar chart, box plot, and histogram. And also we discussed about skewness and kurtosis. Okay. So after that, so we discussed about random variable. Okay. Yeah. So before, as part of this, we also discussed about the data types. Okay. So data types also we have discussed as part of the descriptive statistics. So random variable. So we have discussed about the discrete random variable and continuous random variable. Right. And we have seen a few examples as well on the descriptive and continuous random variables. And then we started the discussion on the probability distributions. Okay. So as part of that, we have seen a descriptive, okay, discrete probability distribution. Probability distribution. So under this, we discussed about binomial distribution. So we have seen a few properties of this binomial distribution, and we have taken an example and we have understood. So what are those properties means? And then we have done a probability computation. Okay. So as part of this binomial distribution or discrete probability distribution. Right. So today we are going to discuss about the continuous probability distribution. Right. So as part of that, we are going to discuss about the normal distribution. And then again, so we will see how to compute probability. So when it comes to the continuous random variable, that is nothing but the normal distribution. A specific example of continuous probability distribution is normal distribution. We'll see the probability computation as well. Right. And also we discussed about the Z scores. Right. So this is what actually we have discussed till here, and we're going to discuss the normal distribution, and we're going to see the probability computation when it comes to the normal distribution. Right. All right. Normal distribution. So normal distribution is one of the most famous statistical distributions. Okay. So the normal distribution would be constructed upon a continuous random variable. So when the random variable is a continuous random variable, so we know, right? So there are two kinds of random variables. One is a discrete random variable. The other one is continuous random variable. And when you say a random variable is a continuous random variable, so if that random variable is constructed upon a continuous data type, then that is called as continuous random variable. Okay. So examples, the time it takes to complete a race. So how much time? We do not know how much time does it take. And the time being a continuous data type, yes, so that can be called as continuous random variable. And if you have a probability distribution on this continuous random variable, then that is a continuous probability distribution. And as part of this continuous probability distribution, we are discussing the normal distribution. Okay. So for example, so the heights of people, okay, are normally distributed. And also the blood pressure levels. So if you take the most of the natural phenomenon, like if you talk about the population data, heights of the people or the blood pressure levels of the population, so tend to follow the normal distribution. Okay, right. So similar to the binomial distribution properties, so when do we call a data follows the binomial distribution, or when do we say that an experiment is a binomial experiment? So it has got certain properties. So 4 to 5 properties that we have, and we have discussed, right? Similar to that, even the normal distribution also has got a few properties. And if you have to call a data set follows normal distribution, then the data should satisfy these properties. Okay, and let us understand these properties one by one. So a continuous random variable x, okay, so has a normally distributed. So if it values fall into a smooth curve, that is bell-shaped curve. So what does it mean? If at all, if I plot a histogram for the data that we have, so it should follow R. So all the data points should form a bell-shaped curve like this. Okay, so this is a normally a distributed data, you can say. So this is one of the properties. And every normal distribution has its own mean and standard deviation, meaning a normal distribution can be characterized by mean and standard deviation. See how humans, so we have a label or how we have been characterized by name and other things. Okay, so how we find ourselves as a unique. For example, how can I find yourself as a unique? Probably I can have your first name, last name, and middle name and date of birth. Okay? So these things, so with these things I can find you as a unique person, so in the world, for example. And how a normal distribution can be find out as a unique based on mean and the standard deviation. Based on these two parameters, so we can find out a normal distribution as a unique. That means, so a normal distribution is characterized by mean as well as the standard deviation. That means if I have the mean and standard deviation, I can generate all the values. So that satisfies so these two parameters. So that data follows normal distribution. Okay? And the shape of normal distribution is symmetric around the mean. So here I have a mean. This is a mean. The normal distribution is symmetric around the mean means, so how much the portion to the left side, so is there the same portion will be there to the right side also. So that means if I just cut this curve, so exactly in the mean, so I would get two equal halves. So that is the symmetric around the mean. And the mean, median, and the mode of a normal distribution are equal. Okay. So if I find for this data, mean, okay, median, and mode, so will be equal, will be, so fall on same number. The same number act as a mean, median, and mode. The area under the curve is 1. So if I find, so the area under the curve, the integration of, so from here to here of this, the random variable value, so that is 1. So the total area under this curve is 1. Right. And the normal distributions are denser in the center and less in the tails. Okay. So what do you mean by denser in the center? For example, this is my normal distribution, for example, and here we have mean. Okay. And if you see here, the area around this mean is very high. So this area is very, very high. That means, so around this mean, the normal distribution are denser. And as you move towards these tails, okay, so these are called as tails, right? So as you move toward these tails, so the density is going to be decreased. What do you mean by density? The area under this curve, area. Okay, so this is going to be reduced. So that is another property of the normal distribution. As you move towards the tails, the density would be less. So as you move toward the mean, the density would increases because of the more number of values tend to occur around the mean. So in this normal distribution, right? So these are some theoretical properties. Now, so we have a few empirical properties also, empirical rules. Okay, what are these empirical rules? So based on the experiments, so these rules have been identified. So what are those rules? So we have 68% of the area of a normal distribution should be within one standard deviation. 95% should be two standard deviations. 99.7% should be within three standard deviations, right? So let us understand with an example these empirical rules. So let's say we have collected the age details of, yeah, so age details of the people who are living in our neighborhood or the people who are living in our apartment complex. The age details are like this. So 20, so 20, 25, 30, 10, okay, 50, 38, 39, 26. So like that we have collected for 100 people. Okay, 100 people. When I compute mean for this data set, the mean mu is, let us say, 30. Okay, and so I can compute standard deviation also, right? For this, the standard deviation, let us say, for example, sigma. So sigma is 2. Right? So these are the mean and the standard deviation for the data set. Okay, now the empirical rules are like this. Let me draw a bell-shaped curve here. Right. Now here we have mean. So this is mean mu. So how much is the mean for this data? 30. So that is what 30 here. Now standard deviation is 2. Okay. So I can mark these standard deviations like this. So in the curve like this. So this is, so minus 1 standard deviation. So, right. So if you compare with normal curve like this, for example, okay, so a standard normal curve, this would be 0. So below 0 will have a negative 1, negative 2, negative 3, and these are positive 1, positive 2, positive 3. So to what extent these values will be there? So this is plus infinite and this is minus infinite. Okay. So at minus infinite, so this curve touches the line, and positive infinite, this curve touches this line. Okay. So now, so here mu minus sigma. Okay, and here I can mark mu plus sigma here. So this is called as mu plus or minus sigma. This band, okay, this is called as mu plus or minus sigma. mu plus r minus 1 sigma. Now, as part of this empirical rule, 68% of the data points should fall under in this region. Okay? So let me construct a band here, mu plus r minus sigma plus r minus sigma. So I'll get the two values. So one is with minus 30 minus 2, mu minus sigma, that is 28, then 32. So this is the band that we are talking about here. So this is 28 and here we have 32. Now, so as per this empirical rule, so 68% of the data should fall under with this age category, 28 years to 32 years. Now, so out of all these people, 100 people, okay, so 68 people age should be between 28 years to 32 years. So this is the first empirical rule. So from your neighborhood or from your apartment complex. Okay. The second one, mu plus or minus 2 sigma. So that means, so let us compute this. So this is 26 and 34. Then mark these data points, 26, 34. Okay, so this is here and we have here. So 26, 34. So 95%, let me change the color here. Yeah, so 95%, so of the data should fall under between these two values, that is mu plus or minus, this is minus 2 sigma, this is mu plus 2 sigma. Okay, so mu plus or minus 2 sigma, that means from mean, so 2 standard deviations away, so how many data points should be there? 95% of the data points should be there within these ranges. That means out of 100 people, so 95 people age should be between 26 years to 34 years. Okay, so then the third empirical rule is this. So third empirical rule is, let us compute the band now. Okay, mu plus or minus 3 sigma. So that is 24, 36. Okay. And here 24, 36. Now, how much data should fall, how much percentage of data should fall under in this region? So 99.7% of the data should fall under, so within this region, that is mu minus 3 sigma, mu plus 3 sigma. Mu plus 3 sigma. That means, so 99.7% of the people age should be between 24 years to 36 years. That means almost all of the people. So 100% people, almost, when I say 100%, 99.7% again. Yeah. So people age should fall under in this age band. So then we can say that, yes, so this data follows normal distribution as per the empirical rules. So all these three conditions should be satisfied. 68% of the data should fall under, so between 28 years to 32 years, and 26 to 34 plus or minus 2 sigma. So plus or minus 3 sigma, 24 to 36 years. Okay. So if at all any data follows, so this notation, so here 68%, this is 95%, and this is 99.7%. So any data that follows these empirical rules, then you can say that data follows normal distribution, right? Okay. And another method or another way to find out the outliers, so let us discuss. So we have discussed how to find out the outliers in the data. So we discussed about the box plot. So we can also use, so this empirical rule to identify the outliers in the data set. I can construct a band like this, for example. So I can construct a band. This is a mean, mu, and so I can construct a band mu plus 3 sigma, mu minus 3 sigma. Okay. Okay. And then, so I can just mark all the data points. So in this band, any data point, for example, that goes below this mu 3 sigma, that goes above mu plus 3 sigma like this, then I can consider them as outliers. Okay, outliers. So that means 99.7% of the times, any data that comes from the normal process should be between mu plus r minus 3 sigma. That means these data points, if at all, if you are so talking about a normal kind of a process, a general process, if at all those data points are generated so in a proper manner, those data points should fall under within this region, and any abnormality is there in the process, that means the process is not under control. So you talk about any operation, yes, any manufacturing process or any data collection process, for example. So the data points goes beyond so this region, then you can term as outliers. So this is another methodology to find out the outliers from a given data set. Right. Okay. Right. It can go, yes. So more than 3 sigma marks as well. That's right. Right. So pictorial representation of whatever we have discussed. The normal distribution is symmetrical around the mean. Right. So this is a mean, and 50% is the left side and 50% is the right side. So that means, so if I cut this curve, this distribution exactly on the mean, so then I'll get the two equal halves. And the median, mean, and mode happens to be on the same number. So the mean is equal to median is equal to mode. Okay. So that is the theoretical the properties for the normal distribution. And when it comes to the empirical rules, as we have discussed, mean plus or minus 1. So within this range, so we should have 68% of the data within the one standard deviation, and 95% of the values should be within plus or minus 2 standard deviations. And here we have 99.7% of the times our values should be within plus or minus 3 standard deviation. So these are the empirical rules that we have discussed. All right. So now let us say, so how do you compute the probability in case of continuous distributions? Okay, so now let us see that. So in case of continuous distributions, okay, so we have to follow a different method than the discrete probability distribution. If you recall the examples that we have discussed, so on the electronics showroom, so we have computed what is the probability, the average probability that how many number of TVs can be sold in that showroom. And we have been given the probability distribution table like, okay, so we have been given a table. If you recall, let me go through that otherwise. So this is, yeah, this is a table that has been given to us. Right? And here, how do we compute the probabilities? So just what is the probability of selling a TV? Okay, so probability of selling a TV is equal to how much it is 0.40. Straight away we can compute using this table. And probability of selling at least, okay, so at least one TV. So we can say that we can add all of these things and we have said that how much it is 0.6 like that. Right? So since this is a discrete probability distribution, we can find out the probabilities for these discrete values. At 0, how much is the probability? At 1, how much is the probability, like that. But in case of continuous distribution, so this kind of the interpretation will not be possible, because, for example, let me go back to that example. So let us say, so I want to find out the probability of the raining tomorrow exactly, let's say 2.3 centimeters. Okay. So raining tomorrow, my random variable is raining, okay, tomorrow. So I want to find out what is the probability that tomorrow the rain would be exactly 2.3 millimeters. Okay. What is the probability here? So let us see that. Now what we can do is, so I can take this rain as a random variable. I can construct a distribution like this. So this is my distribution, a continuous distribution. Okay. Now let us see this is the mean of this distribution. The mean value is, let's say for example, 2. Okay. Okay. Now here the 2.3 falls here, for example 2.3 is here. So I can mark. So the probability under this area is how much under this curve. So is area how much, so that value is occupying. So if you want to find out, so the probability in this curve, so how much area, so that value, the random variable value is occupying. Now since 2.3 is I can represent as a line here. So on this scale here, a line I can represent. And what is the area of this line? The area of a line is 0, because so the line will have the height but doesn't have any width. The area of this line is 0. That means the probability of the raining tomorrow exactly at 2.3 millimeters is 0. Let us say what is the probability of raining tomorrow, let's say so 1.9 millimeters. Okay. So that also will be 0. So here I have 1.9. So this also a straight line, I can say. So it occupies a straight line, and straight line area is 0. That means in a continuous distributions, the probability value associated with a single value is always 0, because that occupies a straight line and the area of the straight line is always 0. But how do you compute the probabilities in case of continuous distributions? We'll go for ranges. That means what is the probability of raining tomorrow is more than 2.3 millimeters, or less than 1.9 millimeters, or between, so more than 1.9 and less than 2.3. That means always we'll go for ranges. That means what is the probability that the raining tomorrow is more than, so 2.3. So in that case, what I would do is I'll find out the area to the right of 2.3. This area I'll find out. Then that gives me what is the area. So the area is basically the probability, right? So this is the probability that the rain tomorrow would be more than 2.3 millimeters. Similarly, so less than 1.9. Find out to the left side of this. So left side of this, so this is the area that is nothing but the probability of tomorrow rain is less than 1.9 millimeters. Okay? Or I can find out between these two. Okay? What is the probability that the rain would be more than 1.9 but less than 2.3? Find out the area between these two values. Okay, this is the area, so that is a probability we are going to find out. Okay, remember in case of continuous distributions, the value associated with a single value, the probability associated with a single value is always 0. We will go for the ranges are intervals. So that is what we'll go for in the continuous distributions. But wherein in the discrete distributions, yes, it is possible to find out a probability associated with a single value. As we have seen, the probability of selling a TV, right? So how much it was, our probability of selling no TVs, so 0.40. So we could find out the probability associated with a single value like this. Okay, but so that is not possible in case of continuous distribution, because so the reason that we have discussed. All right. So how do you find out this the normal distribution probability in case of continuous distributions, or in case of normal distributions? How do you find out the probability? So we can find out the probability using Python. So we have a package called SciPy. So this is a package, scientific Python or SciPy. And from this, we would import a module called stats. Stats is a module. Okay. So in this stats, so we have the method nar, so CDF, cumulative distribution function. Then we will mention the random variable value. The location is equal to the mean value of the data set, and the scale is nothing but a standard deviation. Okay, so we'll see one example on this. So how to compute the normal probability for a given problem. Right. So here is an example. Okay. So the example here is find the probability that a normally distributed random variable has a mean of 60 and a standard deviation of 10. And we would like to find the probability that x is less than 70. Okay. So let me put in a different manner. So this example, let's say we have 100 students in a classroom and we have collected the 100 students marks. Okay. The first student mark, let's say 60. Okay. Second student 80. Okay. 90. Okay. 40. So 95. So like that we have collected for all 100 students. Now, so when we compute this 100 students average, so that average is 60. Mean is equal to 60. Right. And the standard deviation. The standard deviation is 10. So I can compute standard deviation for this, right? Yes. So that is 10. Now the question is, if I pick a student randomly from these 100 students, what is the probability that that student will have the score less than 70 marks? That means if I pick one student from the group of 100 people, what is the probability that this student will have the score less than 70? So this is what actually we have to find out. The random variable is x. So this is a student randomly. If I pick a student, what is the probability that this student will have the score less than 70 marks? That is what I want to find out. And for that, so they mentioned that in the problem. So these scores are reasonably modeled with a normal distribution. That means this data follows the normal distribution, and we can apply so this formula to find out so how much is the probability. And precisely what we're trying to do here is, so this is my distribution. Okay, so this is my distribution. Let me. Okay, and this is a mean here. What is the mean of the distribution? 60. Standard deviation is 10. Okay, now what I want to find out, I want to find out the x is less than 70. Okay, so I can mark 70 here. Now I want to find out the area to the left of 70, because I want to find out the probability of the random variable which is less than or equal to 70. This is what I want to find out. So that means I want to find out the area to the left of this. So that is from minus infinite till this 70. So this area I want to find out. Okay, now let us see how we can find out this area in Python. Let me open Python environment. Just give me a minute, guys. Let me open that. Right. So this is the Jupyter notebook. So these are the packages that we need. SciPy import stats. And so this is a command. So x is nothing but the random variable value. So how much is the value? 70. Okay. And mean is, so how much is the mean for the data set? 60. So that has been given in the problem statement, and the scale, that is standard deviation, or the standard deviation of the data, that is 10. Let us execute this. The value that I've got is 84%. So that means the distribution that we have here is, so this is 60 and this is where we have 70. The area to the left of this, so how much it is? 84%. So how do we interpret this value, 84%? So that means if I pick a student from the classroom randomly out of 100 students, what is the probability that this student will have score less than 70 marks? Is 84%. That means there is a 84% probability that if I pick a student randomly from the class, so that student will have the score of less than 70 marks. So that's how we can interpret, so this 84%. Okay. Now, one more question. But what is the probability that if I pick a student, so randomly from the classroom, so that student will have the score of more than 70? So what is that area? Where is that area we can find? So that area is exactly the other opposite. To the more than 70 means greater than 70. So that area is this. So this area. So how do you find out this area? See, we know that this area, the total area under the curve is 1, right? So this is the total area. And I know, so from minus infinite till this, so I know that is 84%. And I want to find out from here till positive infinite. Okay. So that means if I subtract this area to the left of the 70 from 1, then I'll get that area. So that is 16%. Okay. So that means there is a 16% probability that if I pick one, yeah, that's right. So if I pick one person from the class, that student will have the score more than 70 marks. Right? So that is 16% is a score, the probability. So that's how we can apply the probability concept. So for these problems. So a few more problems. Yeah. So again, let us go back to our GMAT scores problem. Suppose GMAT scores can be reasonably modeled using the normal distribution. That means the GMAT scores are following normal distribution. The mean of 711 and sigma of 29 standard deviation. And what is the P x less than or equal to 680? So how do we read this, the short form of this equation? How do we read this? What is the probability that the random variable value, that is x, is less than 680? In a more simpler manner, so how we can read this is, if I pick a student from the classroom, what is the probability that, so that student will have the score of less than 680? So that means if you see this is the distribution of our scores, and where we can find 680 somewhere around here, then we have to find out the area to the left, 680. Okay, so this area we have to find out. So this area. So again, let us go back to our Python program 711. Yeah. So this is 680. X value is 680. Okay. And the mean value is 711. Standard deviation is 29. So the value is 14.2. Okay. So this is a 14.2 is a value. So that means this area to the left of 680 . So this area is how much it is? 14.2. 14.2. So this is how we can find out the probability for a given problem. Right. Right. So this is another problem. What is the probability that the value is between 697 and 740? So this is my area. Okay. So this is a distribution. And here we have 711. This is a mean value. And I want to find out if I pick a student randomly, what is the probability that that student will have the score between 697 and 740? That means 697 is very close to mean. So this is 697. 740 is somewhere around here. 740. Now I want to find out the area between these two values, this interval. So how can I find out? So there is no direct method to find out this area. First, what we have to do is find out the area to the left of 740. So this area we have to find out. Then find out the area to the left of 697. So till here. Then subtract these two areas. Let's say this is A and this is B. So first we'll find out this area and then to the left of 740. So the difference between A minus B. Okay, A minus B, that means difference between this and this, I would get this area. So that likewise we can find out, and that is the probability 0.53. And we know how to find out to the left of the probability to the left of given value. So the stats, what are the Python code that we have seen so far. So we can apply simply 697 and 740. I'll get this area and I'll get this entire area. Subtract these two areas, then I'll get this middle portion. Okay, the range I'll get. So this is 740. So this is 697. So this is the area. So what is the probability? This is 0.84 and this 0.31. Okay. Then subtract this area from this area, I'll get 0.53. That is the middle portion of this area. So 697 and 740. That means there is a 53% probability that if I pick a student randomly, so from the class, so that student will have the scores between these two values. So that's how we can apply the probability distribution, normal probability distributions computations for a given problem. Yeah. So there is a question: can you also add the area less than 697 and area greater than 740? Yes, you can add. But the question here is, so not that we need to find out the area between these two values. So that is what my question is. And if the question is less than 697, yes. So you can find out that you can add that area too. Yes. Right. Now, so the theoretical examples are fine, but we want to find out where we will apply this normal distribution in the real life scenario. Okay, so let us understand the application of the normal distribution, one of the real life scenarios. Right. Now, so we want to apply this normal distribution concept. So in the stock market, okay, and we want to find out, so which company's stock is more attractive to invest. Okay, in investment banking, in the banking and the finance domain. So to give the advice to the customer, in which stock the customers have to invest so that they'll get good returns. So that is a very important task. So for the investment bankers. Okay. So as part of that, so let us evaluate two stocks. Okay, two stocks are basically BEML is one stock. The other one is Glaxo. These are the two stocks that we have taken into account, and let us analyze out of these two stocks. So which stock is more attractive? Which stock is more risk? So if you invest your money, so would be lost, right? So that is a risky stock. and which stock is a safe stock. That means if you invest the money, yes, the growth is also very limited, as well as you will not lose your money. Okay, so that is what we want to analyze. So in a nutshell, out of these two stocks, which stock is a good stock and which stock is a risky stock, that is what we want to analyze using this normal distribution, right? Right. So for this purpose, so we have collected the data of BML stock as well as Glaxo. So from 2010 to 2016. So from BSC exchange. So this is the website. This data is openly available and we can download this data. Okay, so the data that we have collected is 2010 to 2016. This is the sample data. So we have the date, open price, every day. So this is the day, open price on the day. That means when the stock market opens, so what is the opening price? The high on the day. So the high price, okay, and the low price, how low the stock has traded, and the last traded value, the closed. So after adjusting the different parameters, then they'll arrive this close price and the trade quantity and the turnover. Okay, so out of this, so we are interested, so only the close price, okay, and this is the BML stock price and this is Glaxo stock price. Okay. And so we are interested in the close price. Based on this, we are going to understand, we are going to identify whether a stock price, a stock is attractive stock or that is a risky stock. Okay, so let us see that. And so what are the questions we are going to answer using this normal distribution, application of the normal distribution? So we are going to understand, so the daily rate of return of this stock. What is expected daily rate of return? That means the average. Remember, what is expected value of a random variable? Average. So E of X. Okay. So what is the average, the rate of return of these two stocks? And also, which stock have higher risk or volatility as far as daily returns are concerned? So which stock is a risky stock? Okay. And what is the probability that the stock has higher probability of making daily return of 2% or more? That means the profitability of 2% or more and making loss of 2% or more. We are going to find out what is the probability of the BML stock is more than 2% gain, and what is the probability of these two stocks risk of 2% or more. The risk is the negative, definitely that should be in the negative rate of return, and this is a positive. That means, so this one gives us the daily return, so that is a profitable, and this gives us the loss of more than 2%. So that is what we are going to find out, so from these stock prices, right? Now if you say this close price, how do we compute, okay, a return? How do we compute return? Okay, so we'll focus on this column. The gain or return would be computed using this formula. Okay, the gain or return would be computed the close price of T, that means a current day's close price minus previous day's close price by previous day's close price. So T stands for today's close price, T minus 1 is yesterday's close price, and then divide by yesterday's close price. Let us say, for example, we have the prices like this. Okay, close price, so 100, 200, okay, so 300 for example, and 150 like this. The gain, okay, so for this we don't we cannot calculate for this day. So this is a day 1, day 1, day 2, day 3 like this. So for this day 2, how do we compute? 200 minus the previous day's close price, 100, okay, so divided by 100. So this is a gain percentage. And likewise, we'll compute for this day also. This day, so 300 minus 200. previous day price, this by 200, and this is the gain percentage on third day. So likewise, so we are going to compute for all the days. So this is what actually our focus area. So this we are interested in. Based on this, so we can compute the risk associated with the stock, okay, or how much gain we can get so from that stock. So to compute that, so we can use a direct method from pandas. So PCT, percentage change. So in pandas we can compute this column directly. Right. So this is a close price, and we have computed the gain. The first day we cannot compute because we did not have the previous day, right? So that is NaN, not a number. So the second day, the gain is loss. Third day, yes, these are positive. Wherever you see positive values, that means on that day we have gained. Wherever you see negative values, so we have lost some amount on that day. So this we have lost this much percentage. We have gained, lost like that. So these are the percentage of gains. And when you visualize, so this column, gain column, so this is what actually you can see. So it is increasing, decreasing, increasing, decreasing. So wherever you see above zero, so that is the profit for us. Below zero, that is loss for us. Okay, from 2010 to 2017. All right. So you can see there are a very high spike, so sudden surge on that day, and even you can see here. So this loss. Okay. Now, so if you visualize this data, the gain data, whatever the gain data that we have, so you can see here. So we will compute for both stocks. So this is, for example, if you see this is a BEML, and we'll also compute for Glaxo. These two stocks will compute the gain ratio. And if you see the distribution of the Glaxo and the BEML, you can see this distribution. Okay. So based on the color coding, you can identify. So this is Glaxo and this is BEML. And compute for this the mean and variance. For Glaxo, the mean value is 0.0004, standard deviation is 0.0134. So that is the Glaxo, and for BEML this much. And if you see here, the width of the BEML is more. So when you say the width or spread is more for BEML. What do you mean by spread? Guys, recall our variance discussion. More spread, more fluctuations. So directly proportional to more width, more spread. Okay, more spread of the data. More spread of the data directly related to the more width in the distribution. That means BEML has lot of fluctuations. The spread is more. Right? So hence the width of this distribution is also more. And for Glaxo, the Glaxo, this is a positively skewed, okay, because the height is very high in this case, and the width is low. That means the standard deviation or the variance for this Glax is low in comparison to BEML. So that we can see here. So that is evident. What is standard deviation for Glaxo? That is 0.0, so 134, 0.01, and this 0.02. The BEML, the standard deviation is 0.02. Okay. Now the risk, okay, the risk is directly related to standard deviation. If at all there is a high fluctuations like this, that indicates high volatility in the stock market or stock price. High volatility indicates high risk. High fluctuations indicates high volatility. High volatility indicates high risk. That means we have the BEML high risky stock. Okay. And the Glaxo is in comparison to BEML, so this is not so risky product. So that is one answer. So one question we have answered here. Right. So based on this standard deviation, we would say that which one is a risky product, which one is not a risky product. So high standard deviation, high risky product, high risky stock price. All right. Now, if you see the expected daily rate of return. So we also have to find out the expected daily rate of return, right? So is around 0%. for both stocks. So if you see, the mean value is 0.0004, 0.0003. That means the expected daily rate of return, that is a gain, is around zero. That means, so on an average, we are not going to get anything out of these stocks. That is zero. Coming to the variance or standard deviation, for BML, the stock has higher risk as the standard deviation of the BML is 2.64. For this, the width is more, that means high standard deviation, high volatile, the stock price is. That means, so this is a risky product. And on the other hand, so for Glaxo, we have 1.33%. For 1.33%, this is the standard deviation, okay, the width, the deviation of this stock price, and this is not a risky one in comparison to the BEML stock. That means we have answered two questions. What is the expected daily rate of return is zero, and which one is the risky stock? So the BEML is a risky one, right? Now coming to other two questions. The other two questions are, what is the probability of making 2% loss or higher in Glaxo? So how do we find out that? So recall our probability distribution examples. So this was our 711. What we have done, if I want to find out, okay, 740, what is the probability of the random variable is more than 740? What we have done, simply, so we have computed the area to the right of 740, and this is the probability. Similarly here, what is the probability of making 2% or higher loss, so in Glaxo? So that means we have to find out, so 2% I can write it as like this, 0.02. Since we are talking about the loss, that means this should be negative. Now find out where that the negative 0.02 fits into in this diagram. So here we are talking about Glaxo. So Glaxo is this, the blue color. So here, for example, this negative 0.05 should be to the right side of this. Probably I can say this minus 0.02. Okay, so this is where actually I can mark it. Now I have to find out the area to this area we have to find out, and we know how to find out this area. And this area is how much it is, 0.063. That means 6.3%. So there is 6.3% chance that we would make 2% or higher losses if you invest so in this Glaxo stocks. And probability of making 2% or higher loss, so in BEML. Now coming to the BEML. So this is a BEML. Now you see this. So for the same area, so this is negative 0.02. So this is the area. The area is more, right? For this BEML, then the area must be more. Now how much it is? So probability of making 2% loss or higher in BEML is 22%. Since the area is more, the risk is also more. 22% is a risk if you invest. Okay, so in this BEML, so there is a chance of making loss or 2% minimum, at least 2% loss is 22%. Okay, now coming to the gains. So last we have answered. Now coming to the gains. The probability of making 2% or more gain in Glaxo. So 2% gain means, so 0.02. This 0.02 to the right of 0, we have to mark it like this, for example, here. Okay, 0.02. So this is the area we have to find out. So how much is this area? 7.1%. That is 0.071. That means if you invest, so in this Glaxo, so the probability of making 2% gain or more is 0.07. Okay. And coming to the BEML, yes, so this area we have to find out, okay, where we have more area here, this area we have to find out. So this area is how much it is? 22.76. That means the BEML has higher probability for making losses as well as higher probability for making gains also. That means, so this BEML is a highly volatile stock. And so this Glaxo is the safest stock. You will not lose much money, or you will not gain much money. Right. So that's how we can analyze using this normal distribution of these various stock prices, and you can understand which one is a risky product and which one is non-risky product. Right? So that's how we can understand. Now let me show you this in Python. Some questions here. Few questions, right? So for Glaxo, yes, so that is a positive kurtosis, right? Standard deviation is less than a less volatile, yes, that is correct. So what do you mean by standard deviation is less? That means less fluctuations, low fluctuations. Low fluctuations translate to low spread of the data, less spread of the data. When you say the spread is low, then the standard deviation is also very low. Okay. How to find out the area? Yeah, so I'm going to showcase that, and yeah, let me show you how to do this analysis in Python now. Let me read this data, BEML CSV. Okay. Right, so this is the data set where we have loaded, and this is what actually our interested column close, right? And similarly, let me load Glaxo. So this is the column where we are interested in. Now let me extract only this column as well as the date column from this data frames, because only those two columns are needed for me. Okay, so like this. So I need only date as well as the close column, and I've discarded all other columns from the data set. And so this is just a data pressing step to make the date as index, right? So date and close the price for the stock, and plot. Okay. So this is a close price. So whatever the data that you have, just a line plot. You can see here, this is a line plot. Okay. And even for the BEML, let us plot it. You can see there is a lot of, yeah. So going up and going down. So it's a valley, then again going up and like this. So that is where actually we're talking about highly volatile, right? And we are computing the gain. So using PCT underscore change. So this is a gain percentage for BEML. Okay, and drop. So we have NAN, right? So just drop this NA value from both of these data sets, right? Then let us visualize the gain, percentage. So for this is for Glaxo. Yeah. So this is the gain percentage for BEML. This for Glaxo. Yeah. So these are, we can plot the histogram or the density plot. Yes, so here we have a 0. And similarly, let us plot for the BEML as well. So it's a density plot. So if you compare, okay, both of these two, so you can see that actually, so the width of this is low, the width of for BEML is very high in comparison to this Glaxo one. Then compute the mean and standard deviation. How do you compute? So using this dataset dot mean and dataset dot standard deviation. So these are standard commands, and mean is 0.0004 and 0.134 is standard deviation for Glaxo. And for BEML, let us compute. Yeah. So this 0.0264 where the deviation is more in BEML. Now, so coming to finding out the probability of making 2% or higher loss in Glaxo. The same formula we have used. Okay, so this is so equivalent to this. Okay, if you have to represent in a pictorial format here, so these are distribution. The mean is around 0 here, and I want to find out the area to the left of 0.02. Okay, so this is where actually I can mark 0.02, for example, negative 0.02, negative 0.02. And so which area we have to find out? I want to find out which is more than, so to the left of this. Okay, so this area, so we want to find out, and this area is whatever we get here. So 0.0635. So that is 6.3%. So is area. And similarly, so how much is the gain? Okay, 2% or higher. So that is 7.1. Okay. So that's how actually we can compute the probabilities. So for a given value, and we can so apply this for the like this real life situation. All right. Okay. Okay. So we'll take a break now, a 5 minutes break. So then after that, we are going to discuss about the inferential statistics. Okay, so far what we have discussed is as part of descriptive statistics and the probability distributions we have discussed, and now we are going to discuss about the inferential statistics. Okay, yeah. So it's 611. So 616 we would start our discussion again. Yeah, hello all. Let us continue our discussion. Yeah, few questions wrote it to me personally, privately. Right. So, where do you download this Python and how to open this Jupyter notebook? Let me give you quickly that information. So, just go to this site. So, I'll post in the chat window as well. So, Anaconda. So, once you go there, scroll it down. Okay. So, till you see this Windows, Mac OS, and Linux. So Python, so if you're using Windows, so you can download this. Just click on this, you'll that will be downloaded. And if you're using Mac OS, just go ahead and download this. Okay. So what are we doing here? When you download this, you are downloading Python. Okay. Different IDEs and some other tools also you are going to download. So this is Anaconda distribution of Python. You don't have to install a Python separately. Just once you download this, just install it. Installation is a pretty straightforward. Just click next. So then Python, the Anaconda would get installed. So once it is installed, just search Anaconda Navigator in the search bar, or you can go for the applications and you can find out a symbol like this. This is Anaconda Navigator. You see this? So just click on this. So if you click here, then it opens this window. And so the Python, the IDE or Python notebook that I've shown you is this Jupyter notebook. If you click here, so we'll get that window. Okay. So when I click here, right. So these are the Python notebooks. And if you want to create a new notebook, click here. So Python 3. Right. So these are the cells, so which are executable cells. So you can write program here, and if you want to execute the program here, so you can click on this run. So like that. So you can execute the cells one by one, and this is a very convenient way of executing the cells, and you can check then and there instantly whether the code is working fine or not in that cell, and you can make the corrections. You can move on. So like that. So you can use this Jupyter notebook. Okay, fine then. So let us go ahead with the inferential statistics. Now, first of all, let us understand. So what do you mean by inferential statistics? Okay, where do you use this? Yeah. So where do we use this inferential statistics? Okay, let us say, for example, so I want to find out the average age, okay, average age of Indians. Okay, so I think we have taken this example last week, but let us again discuss the same example just to refresh our knowledge on the inferential statistics. So how do you find out average age of Indians? So this is a population, right? If you consider India, so here is a population. Now, what is the brute force method? A naive idea to find out, a naive procedure to find out the average age of Indians. So one way is, so I can go and ask each and every person who is living in this country, India, and record the age. Let's say first person, okay, 25. Okay, so 42nd person, okay, 1 year, right? So 70 years, like that. Ask each and every person and take the average of that. So that average, so you'll get it. Okay, so that is here. that is the average of this population, that is average age of Indians. Now, do you think this is possible for a company? Okay, so if you ask me, is it possible? Yes, it is possible. But as a company, so this is not a viable option for the companies. So it requires a lot of energy, money, and time to compute the average age of the Indians. Okay, this is also not a feasible solution, first of all. Okay, then what is the way to find out the average age for the Indians? How do we estimate? Okay, so that means, so what I can do is I can approximately estimate, if not exact value, I can approximately estimate the average age of Indians. When it's approximately estimate, probably I can come up with some kind of a range, for example. So within this range of values, yes, average age of Indians would be there. So that means I want to estimate this population parameter. So this is called as a population parameter because, so this average value. Average is nothing but the mean. Recall inferential statistics. So we call this as a population parameter, that is mean. Okay, this is a mean value. Now, in order to estimate this mean value, what we can do is I can sample the data, for example, sample the data. So instead of going and ask each and every person who is living in this country, so probably I'll take the sample data. So this sample data, okay, so by make use of this sample data, so I would apply, so this inferential statistics. When I apply inferential statistics, so I would get the estimate of this, or I can comment about the population, comment or estimate of the population parameter. That means without accessing the entire data that we have, okay, without accessing the entire data that we have in the population, by just collecting the sample data, okay, sample data, and apply the inferential statistics on this sample data, then, so when I apply the inferential statistics, so we are going to get the estimate of the population parameter, or we can comment based on the business scenario, we can comment about the population parameter. So that is what the inferential statistics. Okay, so in this example, yes, when I apply the sample, when I get the sample data, apply this inferential statistics, then I would get probably the estimation is, let's say, so the average age of the Indians would be between, so 26 years to 35 years. Okay, so this is a range where the population parameter would lie. That means if you follow this method, whatever the value that you get here, so that value would lie within these two values. Okay, and we can associate with confidence or some value how accurate this is. So this is the methodology called as inferential statistics. Okay, let me repeat it quickly. So what is the inferential statistics? So using this sample data, I can estimate the population parameters like this. For example, in this case, we want to find out the average age. And how do you find out average age? So in a normal way, so collect the age details of each and every Indian who is living in this country and take the average. So that is one way to get the right estimate. But this is not a feasible for the companies. This is not a viable solution. Okay? So in order to estimate, even if I get the estimate, even that is also fine for me. I don't need exact value. So all I need is estimation of the population parameter or estimation of this mu value. For that purpose, so what I can do is I can collect the sample data, so from the population, and apply this inferential statistics, then I'll get the estimation like this. So the population parameter or the age of the Indians would be between these two values. This is called as estimation of the population parameter. And if you follow this process, so the value that you get, so would be between these two values, 26 years to 35 years. Okay. So coming up with this kind of estimations or comment about the population parameter, so is all about inferential statistics. So that we can achieve using this inferential statistics. Okay. What do you mean by commenting? We'll discuss that. What do you mean by comment means? Estimation means, as we know, so I can estimate, I can build a range of values within which the population parameter would lie. Okay. Yeah. Right. So inferential statistics is all about, let us say we have the population data like this. Okay. For this population data, so I want to find out the mean value, let's say average weight, or average height or the average age of this population data, that is mu I want to find out, population mean. Okay. So generally I'll have to find out all this population data, the age, for example, this person's age I have to find out, this person, then take the average. So that is the population parameter. As we discussed, so this is not possible for us. Then what we do? A random selection. Take the sample data. So from this sample data, this is my sample. So on this sample, so apply, so this inferential statistics. When I apply inferential statistics, I would get the estimate of this mean. Estimate of this mean. Okay. So that's how actually we can use this inferential statistics. Right. So before we get into this inferential statistics, so let us discuss the important concepts. So what are the examples of inferential statistics? The examples are confidence intervals, CI, so hypothesis testing, and analysis of variance, ANOVA. In short, we call this as ANOVA. So these are all the examples of inferential statistics. Right? So we'll see. So if you have examples of this confidence intervals, of hypothesis testing, and ANOVA, we'll see that. Okay. Before we get into these techniques, so let us discuss a few important concepts related to inferential statistics. Right. So as part of this inferential statistics, so we thought of taking sample, right? Right. So this is my population, for example. So from this population, if I take a sample, I want to find out, let's say, average height of Indians, for example. Okay, average height of the Indians, I want to find out that. So this is my population. From this population, we thought of taking some sample, right? Sample I have taken. This is sample 1. So for the sample 1, okay, when I say sample, what do you mean by sample? Sample is a few data points. Okay, a few data points if you collect, that is called as sample. That means, so I've taken this person, the average height, let's say, okay, 5.2. So this person average height, let's say 5.9. So this person average height, let's say 6.1. So like that, I've taken the sample 1. I've taken the average of the sample data. This average of sample data, so came out to be, let's say, for example, 5.8. Now, based on this information, can I say the average Indian's height is 5.8? Can you see that? Could you please post your answers in the chat window? Okay. Yes, yes, yes. Right. Now let me discuss this. See, this is one sample I've taken. Let us take one more sample. Let me take one more sample. So when I say one more sample, I have collected few other people details, or it is a combination. Again, I have taken a random sample of the average height. So now I have got the values like this. Okay. So 5.3, okay, 5.4, 6.1, like that I have got it. Okay. Now, so if this is sample 2, if I compute the average for the sample 2, would I get exactly the same value of 5.8, or would I get a different value? Could I get exactly same as 5.8? I may not. So because randomly I've sampled, this is sample 2, I might get, let us say for example, so 5.5, that is sample 2. Let us say one more sample I've taken. So this is just a random sample. There is no condition, there is no other sampling method, just have taken random sample, sample 3. So would I get exactly the values of this or this? No, I would get different value. Let us say this is 5.9. So if I change my sample, I'm going to get a different value. But how do you suggest actually? What is the average height of Indians? Would you say 5.8 or 5.5 or 5.9? right? So we cannot conclude based on the descriptive statistics. We cannot conclude. Okay, so we cannot conclude based on the sample statistics. I cannot say the Indian's average height is 5.9 or 5.5, 5.8. Now, important the concept, guys, just pay attention here. There is a quantity, there is one quantity, okay? So it is taking multiple values, okay, multiple values. And for each of these multiple values, I can associate some probability. Okay. So what is this quantity called? So this quantity takes multiple values for each of this value. So I can associate a probability or likelihood. So what is this quantity called? A random variable. Absolutely correct. A random variable. Now you see here, so this sample mean, the sample mean, right? So 5.8, 5.5, 5.9. So the sample mean is taking multiple values. Okay, sample mean is taking multiple values like this. For each of this value, I can associate probability rate. What is the probability of getting the sample mean out of these three? 1 by 3. And what is the probability of getting this 5.5 out of these three values? Again, 1 by 3. This also 1 by 3. That means, so the sample mean is satisfying a criteria of random variable. That means the sample mean is a random variable. Okay, so based on the sample means, we cannot take the decisions because there is uncertainty involved in the sample means. What do you mean by sample means? Sample mean is nothing but descriptive statistics. So as part of descriptive statistics, whatever the data that we have got, so yes, we have computed so the mean for the data set, and the mean for the data set is nothing but the mean, right? So based on that, you cannot take the decision, you cannot conclude the decision because that sample mean is a random variable. If you change the sample, yes, so you are going to get a different decision, different value. And so based on the sample mean, are you going to change your decision? No, right? Decision cannot be changed. Once you take the decision, yes, that should be consistent across the multiple scenarios. But here, as you change the sample, you'll have to change your decision. You have to change your business decision based on this. That means based on the sample means, we cannot take the business decisions because that is a random variable, uncertainty involved in that sample mean. Right. Then what is the way? Inferential statistics. If you want to estimate, the mean of the population, just take sample, apply this inferential statistics, then estimate the population parameter. Then based on that, you can take the decision. But just a sample mean gives you the idea about the sample, but doesn't give you the idea about the population, doesn't use that for the business decisions. Yeah. So inferential statistics we discussed. Right. So one more important theorem in the inferential statistics, so is this central limit theorem. Okay. Right. So central limit theorem is the backbone of the inferential statistics. Okay. So let us understand what is this the central limit theorem or CLT theorem. Okay. Let us say I have a population here. Okay, population. So from this population, I have sampled. Okay, so a sample one. Okay, so this sample one. So when it's a sample, so let us get the terminology right first. Sample is a data set. Sample is a data set. Okay. Sample size is number of data points in this data set. Number of data points, number of rows. Okay, number of data points. Right? So when you say sample one, so in this we have multiple data points. Let us say we have 100 data points in this. For this 100 data points, I can compute mean, right? So this is my sample mean. This sample mean one. Then similarly, I have taken one more sample. This is sample two. Again, here we have 100 data points. So here also we have sample mean. I have computed sample mean. This sample mean too. So like that, I have taken several samples, sample n. So for this, we have means as well. Sample mean I, so and so. Okay, sample mean n. Okay, so then what the CLT theorem says is, so if you take multiple samples and compute these sample means, the CLT states about the distribution of the sample means. The distribution of the sample means would be normal. So if you see, the distribution of the sample means would be normal if the population, the distribution is normal. If this is normal, then your sample means distribution also would be normal. That is first condition. The second condition is, or second statement, not condition, second statement is, even if your population, the distribution is not normal, still your sample means distribution would be normal. Okay? Let me put in a different manner. Does not matter what your population distribution is, if it is normal, okay, or non-normal. Does not matter what your population distribution is. If I take multiple samples, compute the sample means, and the distribution of the sample means would be normally distributed. Okay, that means the sample means distribution does not depend on the population distribution, so it will be always normally distributed. So if at all the population distribution is not normal, then this would be normal if the sample size is fairly large. So that is what the central limit theorem says. Okay, let us demonstrate. So this one, how this would be a normally distributed, right? Let me show you that quickly. Let me open an Excel sheet. Right, so let me generate some random numbers here. This is sample one, you can think of. This is my sample one. Let me think of some random numbers. So right, so here we have how many samples we have? 39. Let me make it as 50. More than 50. Yeah, 63 samples. Sample size is 63. Okay. Now let me draw some 1,000 samples, for example, 1,000 or 2,000. Yeah. So we have how many samples we have drawn here? So we have 2,000. So 192. These are the samples. So sample one, sample two, sample three, like that. Let me populate the data here. Right. So if you see here, so each row in this Excel sheet is one sample, one sample. And what is the sample size of this? 63. You can see here the count is 64, including S1. That means 63 data points are there in each of the sample. And likewise, I have taken how many samples? 2,202. Okay. So these many samples have taken. Now, what this CLT says is, so now compute the mean for each of the sample. Let us compute this mean. So this is mean for first sample, then mean for all the samples. So we have computed mean for all the samples. Okay. Now the distribution of this, okay, this sample means would be normally distributed. So does not matter. So from where you have taken these samples. Now let us see the distribution of this. Let us go for the histogram. So now you can see here. So the distribution of this histogram is approximately normal distributed, right? You can say that. So bell-shaped curve, approximately. Okay. A bell-shaped curve. That means, so if you have the population, what we have done is, so I've taken sample one and compute the mean. Okay, the mean, first mean, take second sample. Each row in this Excel sheet is one sample you can think of. Okay, mean two. So like that, I have taken several means, and the distribution of these means are this. So it gives us the statements like, if you plot this sample means would be approximately normally distributed. So it does not matter what your population distribution is. So that is what the central limit theorem says. And based on this assumption, so we will apply our inferential statistics. So on the sample data, we would assume that whatever the data that we get, that is the sample means. That means that would be normally distributed, and we'll go ahead and apply our inferential statistics, so on the data set. All right, so we'll stop here for today. And tomorrow we are going to discuss about the first inferential statistical technique that is confidence interval. Yeah, let me see if you have any questions. Yeah, attendance link has been posted. So can we access R also in Anaconda? Yes, you can access R as well in Anaconda. Okay, solid. Then we'll stop here for today, and we'll meet tomorrow, and we'll discuss about the next, the first inferential statistical technique. Okay. Yeah. Thank you all. Thanks for joining. We'll